about Kubernetes native streaming applications. My name is Jérémy Frénay. I'm an engineering manager working for a company called Babylon Health. Babylon is a health tech company on a mission to deliver affordable healthcare for everybody on Earth. And we're doing that via AI and machine learning.
Hello, everyone. My name is Francesco, and I'm principal engineer at Nutmeg, a fintech in London, which is delivering a wealth manager solution based on tech. So before we start talking about Kubernetes native streaming application, let's introduce a bit of theory. So what do we actually mean by streaming? Streaming is the process of handling record-by-record data concurrently generated by multiple sources. So this sentence is already quite rich in information. Here, we're talking about processing data, and we're talking about processing data so we can take business decisions by using not the whole data set, but just relying on a single record that we have just received, and potentially all the records that we have seen so far. And all this data is generated by a given number of data sources that is not fixed in time. Therefore, streaming data is data that is continuously generated by a variety of sources. So think about an IoT device streaming data about the temperature in our room. Or if you're wearing a wearable device, the device is constantly streaming data about your heart rate. Or for instance, if you consider metrics and logs generated by your services running in production, these can be streaming data as well. And these are all examples of sources that are constantly generating a flux of data. And from a consumer point of view, in most of the situations, it should not be a problem if there are 2 sources or 2,000 sources constantly generating this data. And that's why we need streaming processing, which are techniques that aim at process streaming data without having access to the full dataset. As we just mentioned, when talking about streaming, we leave the idea of knowing the entire dataset behind. We can see every new record coming in as a new delta on the old dataset. For instance, we could be interested in aggregating all the records that we have seen so far, and then using the extra information we have received to make our next decision. So techniques working on the full dataset may no longer work, given the fact that the dataset is constantly changing. This brings us to the last bit, the streaming application, which is a software solution that applies streaming techniques to process streaming data. So we have our application, and that's where we put the business logic that we need to serve with our solution. The next concept that we need to introduce is our storage layer and the ecosystem that allow us to create those streaming applications. But before I move on, a quick disclaimer. We love Apache Kafka, and that's the solution that we selected for our streaming platform. What is Kafka? Quoting the official website of the Apache project, Kafka is an open source distributed event streaming platform used by thousands of companies for high performance data pipelines, streaming analytics, data integration, and mission critical applications. As you can see, Kafka is adopted by a variety of industry, and that's because of the flexibility of its primitives. So how does Kafka work? The first concept to introduce is the producer that allows us to publish data. The next one is a consumer that can read the messages created by the producer. And all these messages are stored in topics, which are an append-only log distributed across multiple brokers that can be configured to store this message for as much time as we need them. Last but not least, there is an ecosystem of tooling that allow us to import and export data from Kafka and create streaming applications without the need of an extra cluster to deploy them. These two tools are called Kafka Connect and Kafka Streams. Kafka Connect is the tool that allows us to import and export data, and Kafka Stream is a Java library that allows us to create Kafka Stream applications. So please remember these two names because they will appear again in the coming slides. I mentioned an append-only log. We are at Percona Live, and I can see this question coming to our side anytime soon. So, is Kafka a database? I'm sorry, but I'm not the best person to answer this question. But Martin Kleppmann given a brilliant talk at Kafka Summit 2019, if I'm not wrong, where he addressed this question, and I strongly recommend to watch it.
All right. So now that we know a bit more about Kafka itself, we need to introduce the other big K here, and that's Kubernetes. So Kubernetes is an open source project, a container orchestration tool that helps us automate the deployment of our applications, help us scale them automatically, and manage the availability in whatever deployment environment you are. So we could be in the cloud, we can be on-premise, or an hybrid of the two. By the way, it's also the Greek word for the pilot of a ship. Let's go through Kubernetes in a nutshell and introduce some concepts we'll need for this presentation. A classic Kubernetes architecture out there would look like the following, starting with a master node, at least one of them. In this situation, we're gonna actually pick 3 of them to have replication across 3 data centers or 3 availability zones. Those master nodes are managing for us a fleet, a pool of worker nodes. And those are the big machines, the big nodes that are gonna help us schedule and deploy and run our applications. We deploy our applications in a pod, and a pod is basically a wrapper and the smallest deployable unit in Kubernetes, wrapping around your application. And we'll see how it works internally. Other concepts we need to introduce are config maps or secrets, which are objects in Kubernetes that you can use to, well, configure your deployment of your application. If you need to pass some specific configuration for your application in a specific environment, and in the case you need to pass something sensitive like a username, a password, or an encryption key, you can use Kubernetes secret. This state that is generated to configure your application is managed by Kubernetes itself, so meaning it's replicated, is highly available, and fault tolerant. There is one last concept I need to introduce today. And if you think about the secret or the config map I just mentioned, those are some kind of type of objects in Kubernetes. Now, in the recent versions of Kubernetes, they allow us to do something interesting. They allow us to create our own custom resource definition. So think about our own type of objects that can be managed exactly like secrets or config map across the cluster by Kubernetes. This will be useful for us later on today as we talk about how we manage our Kafka topics or Kafka users. One last question. We said we want to use Kubernetes to help us better scale and better manage our application out there in production and be fault tolerant. How do we do that? Well, you might think you deploy your pod with, let's say, 3 replicas, and Kubernetes will automatically deploy it, distribute it across the cluster evenly across different data centers or availability zones in the cloud. And we configure all of those resources, so the deployments of the pods, the secrets, the config maps, the CRDs, with basically some YAML files, some manifest files for our application. Now let's zoom into the Kubernetes pod quickly. We said a pod is a wrapper for our application. We tend to deploy one, let's say a deployment of one pod or many for one specific application. But really, a pod is a group of one or many containers. The pattern you tend to see in the industry is the following, where we deploy in pink our main container, our main application. Today is going to be our stream application. And we can also package together in the same pod some dependencies or some sidecar containers that could help our main container connect to some database, connect to Kafka, bring additional dependencies that we need in this package unit that is the pod. All right, so now we know more about Kafka, about Kubernetes. We can start talking about our use case today. So take the use case of a streaming application, aggregating and processing data, business events from diverse business domains, diverse microservices to potentially serve this processed and aggregated and transformed stream of data to different services downstream. It could be microservice A, which could be handling payments, maybe a Nutmeg, or microservice B, that could be handling our chatbot conversation with our doctors at Babylon. Those services are generating messages, events that we aggregate through Kafka and Kafka Stream applications, and could be up for consumption by a microservice down the line or a projection into a materialized view, such as a search index, for example. The goal today is to focus on the purple items on the screen. So the data itself, the Kafka messages, or the events themselves, and our stream application. And we want our engineering teams to really focus only on this stream application and its development and deployment. But really, in your architecture, in your company, you might look at that kind of diagram. So it's a bit more complex. You have a whole bunch of services producing data, another group of services maybe processing, filtering, aggregating those messages, following their own custom logic, and some services projecting, as I said, those streams into materialized views that can be used for specific use cases. So it could be a search index, it could be a data store for analytics queries, or for long-term storage, like a S3 in the cloud, for example. So each microservice evolves, scales, and potentially can be replaced independently. Actually, your architecture might look even more like this one, meaning not only each team is evolving at their own pace, but they also are free and empowered to pick their own language, framework, technology to fit the use case and to better answer the requirement for their specific use case. So you will end up with microservices in Python, in Node on one side, a bit of Go, some JVM-based languages. You need to adapt. The idea and the goal is still the same here. Your engineering team should be able to focus on the pink box here, and a good platform, according to us, would take care of the rest. The integration complexity would be figured out for them. So if we go back to our use case, what we want to build is a stream application that is easy to deploy and maintain, and hopefully come up with a framework which is repeatable, making this packaged application observable, scalable. And there are a few questions we need to discuss now. First of all, how are we going to package our application? Then how are we going to measure its health? How are we going to measure its performance? Then once we know about the performance and we deploy the application in production, how do we alert properly and manage it once it's out there? We need to also discuss which infrastructure is required in order to deploy this application. And finally, we'll talk about how to manage the resources which are involved in the streaming topology of our stream application. And the idea here is to define a standard that would be used for this deployment, but also in the same way if we were deploying 100, 1,000, 10,000 stream applications. This needs to be built to scale.
So now that we have introduced our landscape, let's start with our suggested to-do list to create a Kubernetes native streaming application. As Jérémy mentioned, we will focus both on the cultural and the technical tricks to help you successfully adopt streaming applications at scale. First come first, containers. So what is a container? Quoting the docker.com website, a container is an image, a lightweight standalone executable package of software that includes everything needed to run an application. And as Jérémy mentioned before, to deploy a pod, we do need a Docker image. And during our journey of building a streaming application, we soon realized that we could standardize a lot in regard how those containers were built. So if we consider two streaming applications serving two completely different business use cases, we can notice that they are pretty much similar. So they both require configuration to connect to the Kafka cluster. They both require a way to expose metrics and report on their health. The only actual difference between these two applications is the code, is the logic that they need to serve the business use case. So if we now consider running 1,000 of different streaming applications, we can see that all the common components have been replicated 1,000 times. And from an organization point of view, this is something that we want to standardize. So the key factor for us has been creating a GitHub template to generate a new stream application. And the template was set it up in such a way that all the boilerplates required to test the application, to deploy the application, were already configured. And alongside the template, we also created a company share library around Kafka Streams. And the template alongside the common library are very powerful tool to drastically reduce the time for to go to production for a new streaming application, because now each team needs to focus only on building the code to serve the new business use case, instead of wasting a lot of time in rebuilding and configuring all the common boilerplates that we discussed it so far. So now that we are able to build something to deploy, the next thing to introduce is a probe. In the Kubernetes world, there are two different types of probes. So we have readiness and liveness probe. The liveness one essentially let Kubernetes know if our application is alive or dead, while the readiness one is designed to inform Kubernetes that the application is now ready to serve traffic. So if we consider a very simple streaming application that consumes some data, maps the value, and write the data back into the Kafka cluster, the liveness and the readiness probe basically can be the same. So we just need to make sure that we can connect to the cluster, and the application is constantly handling new records. But as soon as we change the actual data transformation, the situation gets a bit more complex. So if we now consider a stateful transformation, the readiness probe needs to change a bit. So what does it mean having a stateful application in a streaming context? So think about a counter. So it means having a transformation that relies on a state to keep track of all the previous record that the application has handled before, and it can then use this state to make the next decision based on the new record coming in. So if we consider a Kafka Stream application that counts all the time that a user has visited a web page, for instance, in this case, upon receiving a new record, we need to look up the previous value for the counter and increasing it. So in the Kafka Stream world, the state is stored in an in-memory solution called RocksDB, and all the data that we keep in RocksDB can also be safely stored in a Kafka topic. So the Kafka topic essentially works as a storage layer for the otherwise in-memory data, which means that the next time that we will redeploy the application, we don't lose all the clicks that we have counted before. Which means that we need a way to restore the state, and only when the state is fully restored, we can then start serving the live traffic. And that's when the readiness probe starts differing from the liveness one. The liveness one will report whether the application is connected to the Kafka cluster and if the application is alive, while the readiness should report the application being ready only when the state has been fully restored. So if we consider the counter that I mentioned before, and we consider the situation when we are deploying a new version of this counter, what we want to do is making sure that the old version will be replaced with the new version only when the state is fully restored. So in the situation that this thing doesn't happen, what Kubernetes will do, it will wait for both liveness and readiness to be healthy, and then it will bring down the old application. But if the new one has not restored the state yet, it means that there will be a bit of downtime before we can start serving traffic. While if the readiness was configured to wait for the state to be fully restored, then the downtime could be prevented, because the old instance will still be running, waiting for the readiness to be healthy. And only when the readiness will be healthy, meaning that the state has been restored, the Kubernetes will bring down the old one. In situations where this state is small, you may not see a huge difference in having a specialized readiness probe. But when you start having a lot of data and you're running a scale, the different implementations start adding the value. Essentially, in the situation where restoring the state takes several minutes or even hours, then you need to focus on having a readiness that is reporting on the state in order to prevent any possible downtime.
All right, so now we understand why we need to measure and monitor the liveness, the readiness probes. Let's talk about what metrics we need to measure the performance of our application. So what do we need to measure? For my stream application, the box in pink here on the screen, we need to expose metrics in a standard way. So it doesn't matter which language or which framework we're using. We need to pick one format to expose it could be the performance of the Kafka consumer or the Kafka producer. We need to also measure the Kafka consumer metrics that are extracted from the Kafka infrastructure itself, detecting potential lag. And that means we could see our scaling of the application itself being automated based on the consumer lag or the throughput on this specific service. And we could also measure the Kafka metrics themselves. That means understanding better the overall health of the streaming platform, the infrastructure itself. Okay, so let's have a look at the diagram from the bottom to the top. What we are doing is basically defining using the manifest files we talked about before that are used to configure the deployments of our application. We can use those same YAML files to define metrics exposure and the parsing rules, all using a standard way across all of our stream applications so that each team doesn't have to redefine them one by one. Defining this desired state in YAML means that it will be automatically applied here via CI/CD pipelines, can use something like Flux, which is also a CNCF project. And it will try to apply this desired state to Kubernetes. So that's also why we tend to deploy our Prometheus infrastructure and our Grafana infrastructure for dashboarding with Kubernetes as well, so that we align and we come up with one framework to define the rules for parsing and the dashboards in Grafana from that desired state and that configuration file, all applied via Flux. The idea here is to provide a simplified and standardized template for all developers and all the layers they utilize. So that's basically how they push their application and deploy them to environments, and how do they measure them with the dashboards. So now that we talked about measuring the performance itself, we probably need to alert when things go wrong. And what do we need to alert on? So first of all, the availability itself of the stream application, the performance of this application, the availability of the infrastructure, the Kafka infrastructure itself, and potentially some misconfiguration of the infrastructure. We're going to talk about Kafka topics, which are really the pipelines where events are being produced and consumed. Obviously, there's a whole bunch of permissions being given to users producing or consuming those topics. We can generate some alerts, also detecting potential misconfigurations. So we reuse the same idea of a central single manifest for an application, and a pipeline helping us deploy any type of application, any language, to push alerts, which are defined in two ways. We need to make a clear distinctions between basically measuring the performance, availability of the application, which is really owned by a specific domain owner, a team that really knows about this application and its implementation. And on the other side, measuring and alerting on the health and performance of the Kafka infrastructure itself, which might be owned by a data operations team or data infrastructure team. Those types of alerts are very different, and we tend to create business-oriented alerts for the stream applications, because alerting on let's say the consumer lag of a stream app might not mean much, although alerting on the number of, in our case at Babylon, appointments that are coming to our doctors today, this is more important. This is more meaningful for the domain owner. So we use another CNCF project. We showed Prometheus on screen earlier. We also use Alert Manager, and in the same idea, we configure some default alerts that are basically deployed and pushed from the desired state, applied on the Kubernetes cluster automatically as we deploy our application. But each team can configure their values, meaning they can push and change the thresholds for each of those alerts. All right, so we know about the performance. We alert in production environments, but let's talk about the infrastructure required to deploy this application. So configuring your secure Kafka client can be complex. Francesco and I think deploying a Kafka client should be easy, though. So we need to come up with a way to simplify that process of configuration, deployment, and also alerting for our end users. We need to configure your application with a target infrastructure. That could be DNS record, which backend Kafka cluster is it talking to. We're going to need to configure it with encryption for the in-transit connection, authentication of the access. And in the Kafka world, there are the ACLs, those access control lists to handle permissions. All of those criteria need to be in place before we open a connection. And that tends to be, in our experience with Francesco, it's been a bit complex to let every single team configure their own client. So we had to come up with a solution. So first we thought about, we are deploying pods on Kubernetes with my stream app as the main container. Why not introducing a sidecar container? Enters Kafka proxy. And the idea here is simple. We take care of all the points I mentioned earlier. So encryption, authentication, managing the user access. And we deploy this sidecar by default with your application. Our teams don't need to worry about it anymore. They just mentioned the fact in those YAML files, YAML manifest files, they mentioned the fact they need to use a specific Kafka cluster, and everything gets deployed and configured for them. Now, still, to generate the ping box at the top, the user for my app, my stream applications, this needs to be performed on the Kafka cluster itself, meaning there's a bit of operation here. And in the same way, we need to generate some secrets that are mounted, so Kubernetes secrets that are mounted to our sidecar proxy. So this was an improvement, but we can do better. So we decided to try the Strimzi user operator, basically the Kubernetes operator pattern. And the Kubernetes operator is basically going to use Kubernetes state or Kubernetes events and react to them in order to perform some operations on a remote system. And in our case, it's Kafka. So as we can see now, as our teams are deploying their service with a manifest in black at the bottom, and our CI/CD pipelines are deploying the application, it's also going to apply the desired state that we predefine in the manifest. And here we introduce a new custom resource definition, a CRD, and that's called Kafka user. So we manage the state of this list of Kafka users that we want to see applied on the Kafka cluster. And the Strimzi operator will automatically react to those changes in the state and apply it to the Kafka infrastructure. So at this point, really, we can say our teams only focuses on the ping box and their manifest file, and the rest is being done for them. So suddenly, managing the deployment of a stream app in dozens of environments becomes very easy. It's fully auditable. We abstracted a lot of the complexity, so our engineers can really focus on their domain logic and they don't have to care about the plumbing anymore. And we can guarantee the encryption, the authentication for all of the Kafka clients. We can do even better because we manage this, the way they define those services and these desired states in the manifest. We can set the naming convention in those files for the users. Here we can see kafka.user.myApplication. And we can set the permissions there as well, which is very important for auditability, being able to detect which application has which permission. All right, so we talked about Kafka users, but what about Kafka topics, which are really the most important resource in a Kafka cluster? But again, there is a Strimzi topic operator, which introduces another custom resource definition, the Kafka topic. We manage it the exact same way in our manifest files, automatically pushed, applied to the Kubernetes state via our CI/CD pipeline, and the operator will then propagate this change to the Kafka infrastructure with the right configurations. So it also helps us apply some defaults configurations that we might want across all of our topics. For people operating Kafka clusters, it's important to really make sure we manage the retention configuration. So for how long do you retain data on those topics, the configuration of the partitioning of the topic itself, and the replication to guarantee we are highly available and we can tolerate maybe a faulty partition or a faulty broker altogether. Just like for our Kafka users, we can set the naming convention. We can see here event.domain.a.registration. This is going to be very handy when we manage the permission to allow specific services like service A to only produce to that topic, and my Stream app might be the only application allowed to consume that specific topic. All of that can be written, can be set with the minimum YAML syntax in our manifest and automatically applied to the cluster. What we decided to do is to go even further. Since Kubernetes allows us to define CRDs, and well, Strimzi is already created too here, we went ahead and created an event stream custom resource definition, which defines our own, well, basically our own definition of what a stream of event, a Kafka topic, if you will, is. And we can add some extra criteria or extra fields or properties to that object, basically. And that helped us add the notion of a key, or so the schema for a key or a value that could be interesting to now expose this state in Kubernetes and help visualize all of our topologies in a Kafka cluster. So all of the topics, what is being contained, what kind of data is produced to that topic, and who can consume and produce. So from an engineer point of view, this is how it looks. Using the Kubernetes command, you can list your Kafka users objects. As I said, the state is managed in Kubernetes. We can see our Stream app user there, and we can expect that within milliseconds, really, the operator would have propagated that to the Kafka cluster. We can do the same with our Kafka topics object. And here we can see the configuration that helps also operations team better manage the topics on, as I said, dozens of clusters and environments. And the very interesting part here is, since we have a new type of object, we can list and discover, so it's actually available to anybody, any engineer, to list the event streams, which is really an extension of what a topic is. And you can see here our consumer and our producer for that specific event stream, that specific topic, are directly referring to Kafka users object predefined in our manifest files. So each of those services, service A and MyStream application, have been defined on their side, on their own manifest file, and they created those objects for us.
So last but not least, data lineage. Now that we have a solution to build, deploy, and monitor our streaming application, we need to add a solution to understand, record, and visualize the data in motion. Jérémy introduced the concept of a custom Kubernetes resource to define event streams. And what we realized was that this CRD was not only enabling us to use open source tools such as Strimzi while adding some custom business logic on top, but it was also a very powerful tool to enable a basic data lineage. So one of the most common questions that we received was, my team is publishing data in this topic, but who is actually consuming it? So if we take a look at the graph on the slide, let's say that the team in charge of service A was introducing a breaking change of the schemas that they were using to publish Kafka messages in the stream alpha, and they wanted to understand who were their stakeholders. In this way, they could inform them and organize the change in such a way that wouldn't impact them. So essentially, the team in charge of Service A wanted to understand that there were Service 2 and Service 1 on the other side of the topic. What we realized was that the ACLs could be used to understand the relationship between producers and consumers. And abstracting this idea a bit more, we realized that we had other infrastructure as code around that could be reused to enable the data lineage solution. So the follow-up question for us was, okay, we have all this data, but how long is going to take before it will be out of date? And what we realized was that all this information must be up to date. Otherwise, the streaming applications will not work. So considering the case of ACLs, the deployment of service A must report a requirement of writing on stream alpha. Otherwise, if this information is not there upon deploying service A, the team in charge of service A will start receiving alerts saying that the streaming topology is not working as expected. And that's because Kafka is not letting the service to write into the cluster. So, as Jérémy mentioned before, those CRs are discoverable inside the cluster. And what we have been able to do has been using all these CR in order to build a graph similar to the one that you see here on the slide. So a graph that was allowing us to show all the streams, all the consumers, the producers, and the schema used by each producer to write in each stream. The next thing was enriching the graph with metrics that could help us understanding if the specific section of the data pipeline was receiving traffic or not. So we could understand not only the health of the specific part of the pipeline, but also the load in quite real time. And the graph was built with the idea of providing a tool not only for engineers, but also for product manager and business analyst. So if we consider a product manager that wants to build a new product and he needs to understand what kind of data is currently available, a solution like that can be used to explore what is the data that is currently available in each of the production environments in the situation that the companies have in different production, and what is the traffic, for instance, on each one of those streams. Or if we consider the business analyst, a business analyst that needs to deliver a new report for business can use such a graph to understand what is the data available, or in the case that he needs to understand if the report is not working as expected, he can use the graph to understand the health of the pipeline that is producing the data that he needs. So the key takeaway here is that often there is metadata or other piece of information that, if analyzed with a different point of view, can become a really valuable information for different stakeholders in the business, not only technical stakeholders, but also non-technical stakeholders. So, to summarize, we have introduced a way to build a streaming application, to deploy a streaming application, to monitor and react in case it's not working as expected. We have then added a solution to provision the required infrastructure that we need in such a way that is fully integrated with the deployment manifest of this application. And last but not least, we have baked in a data lineage solution that can be used by the entire organization. And all these things have been designed with the idea of being shared service for every single engineer in the organization.
All right. And since we are at Percona Live today, we thought we would introduce one other use case. Let's take this service A, which is using an RDBMS system to store its data. So you can think about maybe that monolithic application in your architecture that doesn't want to die. We want to allow analytics teams and other front-end products to leverage the events that are produced by this service A for their different use cases. And at the moment, they are stuck in this RDBMS. And ideally, we'd like to reuse the concepts we just discussed. So basically, we need to find a way to turn all the DB insert update statements into domain events that we can stream via our platform of choice, Kafka, and provide to our stream applications that we deployed with the framework we discussed today. So most of you might be already familiar with the notion of change data capture, literally capturing the change data, the difference between two versions of the state in a database row. We can introduce a connector that will read the database binary log and convert the SQL statements into standard Kafka messages. We then can deploy a stream app consuming and processing those raw messages to apply the required transformation that we need in order to output those events in the common format used by all stream consumers in our architecture. Kafka Connect is an open source tool allowing you to deploy a cluster of workers on which you can deploy connectors. So configuring and managing connectors isn't a task we want to see our deployment teams doing, really. So we also use the Strimzi operator to manage the Kafka Connect cluster, the infrastructure itself, deployed on Kubernetes, and the connectors themselves and their configuration. So everything we talked about today, the metrics aggregation, the alerting, the management of the configuration of the users or the topics remain the same, managed from the YAML manifest. But here we can leverage open source connectors such as Debezium, which is a good example of a CDC connector, to perform those common type of transformation for Kafka. And you can go online on the Confluent Hub and see the full list of available Kafka connectors.
So Today, we presented our to-do list to enable engineering teams to create streaming applications at scale by making sure that engineers are only focused on delivering business value instead of wasting time building not very valuable boilerplates. So this is our to-do list, but for sure there are other ways to achieve similar results. And we would love to hear about other alternatives or idea to improve our to-do list. If you have a different approach, please get in touch. We will love to hear about your solution. And here you can find our contact details. Thank you very much for your attention.
Thank you.